Bismillahirrahmanirrahim. Welcome to lecture 5 of Data Communication and Computer Networks. And today we will talk about multiplexing. So we'll talk about multiple techniques of multiplexing. We discuss frequency division multiplexing and time division multiplexing, and we will have examples of both of them. So before we start definition and so on, let's take this example. We have 4 different senders, and these 4 different senders have messages to send. Here they share one link, one common link between them. Okay, so these 4 people will use the same link to send the message to the receivers. Okay, since we have single shared link, we call it multiplexing. So what multiplexing means? I don't have single channel between the source and destination. So there is nothing like here in this image. See here, each computer is connected directly to the other computer. So the sender is connected using separate link, and they don't share the links. However, here in multiplexing, the 4 computers share the same link. Okay, so this is multiplexing, means sharing media. Okay, so in real life, we have links with limited bandwidth. I can have link between each 2 computers, but these links will have limited capacity, limited bandwidth, not enough. So if I want to send big, huge information, it will be very slow. So limited bandwidth will prevent me from sending big messages. So low bandwidth is not good. So what I do in multiplexing, I combine several low bandwidth channels. I combine the channels. I use them together. So I combine several multiple low bandwidth channels to make one channel. At the end, I have one channel with large bandwidth. So instead of having small channels, links with low bandwidth, no, here what I do, I combine all what I have into one path or one media. So we use it to expand the bandwidth. Why we use multiplexing? To expand bandwidth, to have bigger bandwidth. Okay. So here is the definition. If I ask you to define what's multiplexing, so what's multiplexing? Set of techniques, multiple techniques, that allows the simultaneous transmission of multiple signals across a single data link. So I have one link, and in that one link I send multiple signals from multiple senders. I send multiple signals. Okay. It's simultaneous, means at the same time I can send multiple signals into one data link. So simultaneously I can send many signals at the same time using one link. Why we do it? To maximize the utilization of the resources, especially bandwidth. لماذا نستخدم تقنية المالتيبلكسينج؟ حتى نستخدم الباندويث، سعة الشبكة، أفضل الاستخدام الأمثل للباندويث. Okay, so why I use multiplexing? To maximize the utilization of bandwidth and the other resources. Okay, so multiplexing basically is what? Is sharing. Basically is sharing. So multiplexing is sharing multiple links and making them single link. And into that link, we can send as many signals as we want. So here, I have one path for channels. I have one path, one media, but I divide it into 4 channels for each of these 4 senders and receivers. So I have one big path, I divide it into channels, and the number of channels is defined by the signals I'm trying to transmit. So we have 2 types of multiplexing. We have frequency division multiplexing and we have time division multiplexing. Time division multiplexing is divided into 2 categories, synchronous and asynchronous. Usually we use frequency division multiplexing for analog signals, and we use this time division multiplexing is for digital signals. So easy. FDM is for analog signals, TDM is for digital signals. Okay. We start talking about the first technique of multiplexing, which is frequency division multiplexing. Frequency division multiplexing. So how I divide the signals here based on the frequency. Okay, I use the frequency. It's based on frequency. So frequency division is an analog, as we said, technique. We use it when the bandwidth of a link in hertz is greater than the combined bandwidth of the signals to be transmitted. So very easy. The capacity or the bandwidth of the link should be bigger than capacity of link or bandwidth of link is bigger than the combined bandwidth of the signals. So it's bigger than the capacity of the signals, combined signals. I have multiple signals and I need to make sure that the capacity of the media or the capacity of the link is bigger than the bandwidth of the transmitted signals. Signals generated by each sending device should be different. If I have 3 senders, A, B, C, so at the end I need to differentiate this signal is coming from whom. So that's why I have different frequency, different carrier frequency. Why I have different carrier frequency? To know this signal is related to which user. At the end, after modulation, the signals will be combined into big link, into big signal, and it's sent through the link. Okay. Bandwidth ranges are the channels through which the various signals travel. I divided the whole bandwidth into channels. Channels can be separated by strips of unused bandwidth guard bands to prevent signals from overlapping. So I have 3 senders, sender 1, signal 1, channel 2, channel 3. And between them I put space, unused bandwidth. We call it guard band. So I put extra space between each of these and I call it guard band. Okay, I call it guard bands. Why I use it? To prevent signals from overlapping. If I don't have it, then maybe they will overlap like this. I don't have space between them, and this will make too much problems. So I don't want this to happen. That's why I put space, and this space is called guard band. Carrier frequency must not interfere with the original data frequency. So each carrier or each link have its own frequency, and this frequency should not interfere with the original data that's sent. So let's see here. I have three senders. Each of them is given channel. So channel 1, channel 2 and channel 3. يعني عندي 3 قنوات مختلفة بس it's the same link at the end. What I do if I want to send, I multiplex, and the opposite is demultiplexing. Demultiplexing is separating them. So in multiplexing, I combine the signals. In demultiplexing, I separate the signals to give it to the receiver. So frequency division multiplexing with time domain. So see here, each link, each channel have specific frequency. So this frequency is for carrier 1, carrier 2 frequency, and carrier 3 frequency. Different. If you see, this is low frequency, this is very high frequency. So each carrier is given frequency. And this is the message, the signal that the sender wants to send. So these are the sent signals. At the end, I combine these three together. Okay, before sending it, so this is multiplexing. I combine these three together and I generate big signals, combined signals. So instead of sending these three separately, no, in multiplexing I join them together and I send this. So this is done in multiplexing. طبعا why I give different frequencies for each carrier, so I know this is a frequency is related to this computer for this device, this frequency is related to this sender, this frequency is related to this sender, so I can differentiate. Okay, so I combine the frequency of the carrier and the signal I want to send for the three sending devices, and I get these combined signal. Okay, okay. Now I can use frequency domain. That was time domain. Frequency domain the same, but I have a different representation, but the same concept. So I have different carrier frequencies, and I send the signals, and at the end I have this signal, combined signal. Demultiplexing is the opposite. So what I have as input, I have this big signal and I want to divide it. So I do some filtering. I get the signal. I remove this carrier frequency and then I give it to the receiver. So demultiplexing is what? Sharing the big signal, the combined signal, and getting the original data and send that original data to the senders, receivers. The same thing here. I have big combined frequency domain signals. I share them through demultiplexer and I give it to the receivers. Okay, let's take this example here. Assume that a voice channel occupies bandwidth of 4 kHz. See here, each channel has what? 4 kHz. 4. We need to combine 3 channels. How many channels I have? 3. So if I multiply these 3 channels, and each channel is having 4 kHz. At the end, if I multiply, I will get 12 kHz in total. So the total capacity or the total bandwidth of the entire medium is 12. Now I want to share this 12. Okay, I have the data from 20 to 32 kilohertz. So if I say 32 minus 20, how much I get in total? 32 minus 20 equal 12, which is the same as the link. If this is bigger, if this 12 is bigger, if this number is bigger, then I cannot use this media. It doesn't fit. However, here it's the same, so I can send the signal. So if you see an example or a question with something here, so the signals is higher than the capacity of the link, we cannot send it. But here in this example, they are the same, so I can send it. Now, they ask us to show the configuration using frequency domain. Check. Here we need frequency domain. Assume here there is no guard band. No space between each channel, no guard bands. So let's see here. So I have 3 channels. The first channel take signals from frequency 20 and then I add 4. I add to it 4, which is the frequency of each channel, and I get 24. This is the first. I get 24. This is for the first channel. For the second channel, it will take signals from 24 and then I add 4 frequency or the bandwidth and I get 28. And the same thing for the third one. From 28, I add 4 and I get 32. So this is the method. Now if you see here, from 0 to 4 is the frequency of each channel. So here the signals start from 20 to 24, 24 to 28, 28 to 32, and I combine them, and this is the output. In demultiplexing, it's the same concept. I get this big signal, I divide it, and I get. So this is the way how we do it. Okay, let's take the second example. So here in the second example, what we have? Okay, we have 5 channels. How many channels I have? 5. 5 channels. Each with 100, this is 100 kilohertz bandwidth. So each channel is 100, 5 channel, and each channel is how much? Frequency is 100. So I have total is 500. Okay. Are to be multiplexed together. What is the minimum bandwidth of the link if there is a need for 4 guard bands? And each of them is 10 kilohertz. So this is the channel. This is guard band. This is another channel, guard band. Third channel, guard band. Fourth channel, guard band. And fifth channel. So I have 1, 2, 3, 4, 5. And there is space between each 2 of them. So in total I have 4 guard bands. How much is the capacity of the bandwidth for this is 10 kilohertz. So each of them is 10 kilohertz. So if I have this is 100 each, and the guard band is 10 each. So I'll calculate 100, 200, 300, 4, and 500. 500 plus 10, 20, 30, 40. So in total I have 540, which is the minimum capacity. Okay, so this is it. 540 is the minimum capacity or the minimum required capacity. finished talking about frequency division multiplexing. Now we talk about time division multiplexing. So here how we divide based on time. This is close to real life. I have 5 people and these 5 people want to talk, give presentation. So I give each speaker 5 minutes, for example, to talk. I give them specific time and this time is the same. Or we can use different techniques to divide the time. Okay, but time division multiplexing is very easy. We give each device or which connection a specific time. So time division multiplexing is digital process. We use it for digital signals, not for analog signal. Allow several connections to share high bandwidth of a link instead of sharing portion of bandwidth. So each connection will have the entire capacity of the link. Okay? The sender will take the entire capacity. We don't share the capacity here. No, we share the time. Each sending device, we give it some time to take the whole capacity of the link. So each connection occupies a portion of time. It takes some time in the link. The same link is used as in frequency division multiplexing. So it's sectioned by time rather than by frequency. We divide the link based on time. You will see. So here is an example. I have 4 senders. I give each sender some time to use the entire capacity of the link. So for example, 5 minutes for device 4, 5 minutes for device 3, 5 minutes for device 2, and 5 minutes for device 1. But in reality, it's not as big as 5 minutes. It should be less. Okay, so I divide based on time. Okay, so here let's see. I have 4 senders and this one has too much data to send. This one has less data to send, and so on. So I divide it into frames. First frame, only device 1 sent. Okay, this is the one to send. The others still don't have message to send. Second frame, A and D will send. Third frame, A, C, and D. And then this frame, we have all of them have message to send. You see here? And again, all have here message to send. And the same thing here. Okay? So if you see here, this frame, it's not fully utilized. Only I send frame with little on input, because only one has message to send. So why I should give space to all these 3 since they don't have message? So if you see here, this is fully utilized. All devices use the time. However, here, not all of them. So device A will keep waiting until it's sent, which is not good. Okay, so this is time division multiplexing. Demultiplexing is the opposite. So I share here. Very easy. Exactly the same as frequency division multiplexing. So I share the message to the receivers. Okay. For time division multiplexing, we have 2 modes, synchronous and asynchronous, or statistical time division. So 2 names for it. Okay. So synchronous, data flow of each input connection is divided into units, where each input occupies 1 input time slot. So if I have 5 senders, then I have a slot for each of these senders, as we said here. Because I have 1, 2, 3, 4 inputs, then I have 1, 2, 3, 4 slots. The number of input then is the same as number of slots. 1, 2, 3, 4, 1, 2, 3, 4. A unit can be one bit, one character, or one block of data. So the unit we can decide it carries one bit or one character or one block. Each unit becomes output unit and occupies one output time slot. The duration of an output time slot is n times shorter than the duration of input time slot. Okay, so here I have 5 inputs. So frame 1, frame 2, frame 3, frame 4, and frame n. Number of inputs is 5. Number of slots in each frame is 5, as we said earlier. So how many frames? 1, 2, 3, 4, and 5 is the same as the number of inputs. Okay. The problem here, as we see in this example, is empty slots. Empty slots, unused slots. So synchronous TDM is not as efficient as it could be if a source does not have data to send. If the source do not want to send anything, so why should I give him space? For example, if somebody do not want to give presentation, why should I wait for him and he don't have anything? So we will all keep silent. Nobody is sending. The same thing here. The corresponding slot in the output frame is empty. Okay, so they don't have anything to send. Why should I give them a slot? So this is an important issue with synchronous time division multiplexing is empty slots. Okay. To solve it, they propose another scenario, which is statistical time division multiplexing, or we call it asynchronous. In synchronous TDM, each input has a reserved slot for the output frame, which is inefficient if we have no data to send. So this is a problem of synchronous. But the solution here comes with statistical time division multiplexing, or asynchronous. Slots are dynamically allocated to improve bandwidth efficiency. It's dynamically allocated. If I know it wants to send, I give it. If I know it doesn't want, I don't give it. How I decide? Dynamically. When an input line has a slot's worth of data to send, it is given a slot in the input frame. If it has data, then I give it a slot in the output frame. Number of slots in each frame is less than the number of input lines. It uses a method called round robin to decide how is the method to divide the slots. Let's see this example. Number of inputs 5, however the number of slots is 3 here. These I have 5 here, but for example only these 3 want to send, so I give them slots for each of them. So this is the difference here. If you compare between synchronous and asynchronous or statistical, you see here we have empty slots if a device do not want to send. So here, for example, E, D, and B want to send. A and C do not have data to send, and we still give them, which is bad. These are empty slots. This is for synchronous. The other one, E2, D2, and B2. They have to send, so I have only 3 slots. Okay, so here I don't have 5 slots as this one. I have 3 slots. Second time I have D1, B1, and A1. So I don't waste the time at all, which is good. So this is the difference between synchronous time division multiplexing and statistical time division multiplexing. So that was all for lecture 5, and we discussed multiplexing. We came to know two methods of multiplexing, which is frequency division multiplexing used with analog signal, and we also discussed time division multiplexing, which is used for digital signals. And we take examples of how to do these multiplexing techniques. Thank you very much for listening.